Welcome to Chapter 8. The previous chapter covers fundamental concepts and theories related to hypothesis testing. This chapter covers their application by explaining popular methods for hypothesis testing. By the end of this chapter, you will be able to explain what we can use a t-test for and how to do it. Explain what we can use chi-square test for and how to do it. And explain what correlation and regression analysis are. Now, let's see what is t-test and how to implement it in detail. Now, let's dive into the practice of hypothesis testing. First, let's test a hypothesis about a population mean. Suppose we have sample data and we know the value of the sample mean and sample variance. In this case, how can we conclude that the sample mean is greater or smaller than or equal to the population mean? Let's consider by an example. Suppose you are a human resource manager in a company and implement an employee survey. The survey measures employees' motivation by 10 items. Each item is measured by a 7-point Likert scale from 1 equals strongly disagree to 7 equals strongly agree. By averaging the scores of these 10 items, you get the motivation score of each employee. Suppose you only implement the survey for 10 employees. The average motivation score is 4.8 and the variance is 0.16. If the employee's motivation score follows a normal distribution, can we say that the motivation level in your company is equivalent to 5.0? You already know the process of statistical hypothesis testing. Here, we use a two-tailed test. Let's implement hypothesis testing for population mean by following these processes. First, let's specify null and alternative hypothesis. The problem here is that whether we can say that the employee motivation level is 5.0 or not. So, the null hypothesis is the employee motivation level is 5.0. And so, the alternative hypothesis is the employee motivation level is not 5.0. Next, as the second step, let's set the significance level, alpha, to 0.05. In the third step, we calculate the test statistic. In a t-test, we need to compute t-value as the test statistic. And in the final step, we find p-value from t-value and see whether it is below the significance level, alpha. In the third step, we calculate the test statistic. Here, we want to know the population mean, but we do not know the population variance. In such a case, we should use a t-value as a test statistic. We can compute a t-value by this formula. X bar is the sample mean. Mu is the population mean. Small n is the sample size. Small s squared is an unbiased variance, which is an estimated value of the population variance. As the formula suggests, a t-value quantifies the difference between the sample mean and the population mean. Unbiased variance can be computed by this formula. The difference from a sample variance is that when we compute unbiased variance, we need to divide by n-1 instead of n. Here, n is the sample size. Let's plug in the values to the formula. In this problem, x bar, the sample mean, is 4.8. Mu, the population mean is set to 5.0 because we want to see whether the population mean is 5.0 or not. The sample size n is 10. The unbiased variance can be computed based on the sample variance by changing the denominator. It is 0.18. So, the t-value is minus 1.491. As the final step, let's determine whether we can reject a null hypothesis or not. As we use a t-value as a test statistic, we use the t-distribution table here. Since we implement a two-tailed test, we use the t-value for a two-tailed test. The significance level is 0.05. So, we should see the intersection of the degree of freedom of 9 and the significance level of 0.05. The degree of freedom is computed by subtracting 1 from the sample size. The sample size is 10, so the degree of freedom is 9. At the intersection, the t-value is 2.262. Its absolute value is larger than that of the t-value computed in the previous step, minus 1.491. We can reject a null hypothesis only when the t-value specified in the data is larger than the t-value located in the corresponding intersection in the t-distribution table. So, here we cannot reject a null hypothesis. So, the conclusion should be that we cannot say the population mean is different from 5.0. In the example above, we examine whether the sample mean is different from the population mean. That is, we investigate the deviance of the sample mean from the population mean. Let's see the formula of a t-value. The numerator is the difference between the sample mean and the population mean. Thus, it represents the deviance of the sample mean from the population mean. A large t-value means the large deviance. Let's transform the formula a little bit. It suggests that the greater the unbiased variance is, the smaller the t-value is. It means when the population data is widely dispersed, the deviance between the sample mean and the population mean is evaluated as small. We can see it is reasonable by considering these two probability distribution figures. Suppose the red distribution is a sample and the blue is its population. The deviation between the sample mean and the population mean is the same in these two figures. In the upper figure, the population data is more widely dispersed. And we can see, while the sample and the population overlapped in the upper figure, they are separated in the lower figure. It suggests that the larger the population variance is, the smaller the t-value should be, so that the deviance of the sample mean from the population mean will be evaluated as small. The transformed formula also suggests that as the sample size gets larger the t-value is. Let's see these figures. The sample size is larger in the lower figure. As we can see in these figures, as the sample size grows, the sample is more representative of the population, and thus the deviance of the sample mean from the population mean is likely to be smaller. So, if the absolute value of the deviance is equal, it is reasonable to regard the deviance as large when the sample size is large. So, we can say that As a test statistic, t-value quantifies the deviance of the sample mean from the population mean, considering the effect of the population variance and the sample size. Thank you for watching. Please thumbs up and subscribe to my channel.